set, which means that it has some lattice of symmetry. So there is some lattice inside G, and a lattice, the precise definition is a discrete subgroup whose quotient is compact. And if your set A is periodic with respect to this lattice of translations, we say that the tiling is periodic. So these are the basic definitions. Just a couple side remarks. So those are tilings by one tile. You could also tile by multiple tiles. If you have J tiles, F1 to Fj, you can try to partition G into some translates of F1, some translates of F2, and some translates of Fg. And that's a tiling of many sets. You don't necessarily have to tile the whole group. You can also tile subsets of the group, such as periodic subsets of your big group. For pictures, we will normally look at tiling Euclidean space, but many of our results are actually starting set in the realm of lattices, discrete groups. And there's actually quite an interesting question. What is the relationship between tiling in continuous domains like Euclidean space and tiling in discrete domains? And then often it's the location of the tile is not really important. So we often normalize it so that the tile contains the origin. That's a convenient normalization. Okay, so those are the definitions. Let me, it's best to illustrate some examples. So here is an Escher print. And in our language, the Escher print is a tiling of R2, and the tile is a Pegasus. Okay, so there's a single tile, I mean, there are two colors, white and red, but they're both translates of the same object. So you pick any one of these Pegasi, and that is choose that to be your tile F. And this is a periodic tiling. The tiling that used, in fact, I think A is a square lattice in this case. Okay, so this is a tiling by one tile. Here's a tiling by two tiles. Okay, so F1 is a cat, F2 is a dog, and this is a tiling of R2, another periodic tiling of F2 by a cat and a dog. Okay, this is a non-periodic tiling. Okay, so here the tile is a square. Pick one of these squares, call it F, unit square. Now there's a standard tiling of R2 by the unit square. You just a lattice tiling. And so here I've taken a lattice tiling and I've performed one slide move. I've taken one row of the tile and slid it to the right by one. So it was a periodic tiling, but by making this shift, this is no longer a periodic tiling. This tiling has 1 degree, it still has 1 residual degree of periodicity. It's periodic in the respect to horizontal shifts, but it no longer has periodicity in the vertical direction. So the group of periodicity, the period group is not a lattice anymore. The quotient is not compact. So this is only partially periodic. It is not a fully periodic tiling. So this is an example of a non-periodic tiling. And here is, well, it's an art exhibit, but for our purposes, this is a periodic tiling of a subset of R3. So we have a bunch of orange. So here the tile is in orange. And you imagine that you extend this tiling infinitely in all directions. And it will tile not all of R3, but some periodic subset of R3 because there are gaps between the oranges. Okay, so this is a tiling by one tile, periodic tiling of some periodic subset of E. Okay, so these are examples. So hopefully you have some idea what a translational tiling is. Okay, so there's some basic questions here mathematically. So suppose you have a group G, like R3. You take some subset of E of R3 of G, some periodic subset, maybe all of G, and then you take some tau F. And so the first basic question is it possible to tile your big space E by the small tau F? Do tilings exist at all? Okay, so which sets tile the plane, for instance, and which ones don't? Now, for example, squares tile the plane, but equilateral triangles, for example, don't. So we're only allowed to translate the tiles. We're not allowed to rotate the tiles. So a triangle can tile the plane if you also allow rotations, but for this talk, we are only allowing translations. Although a tiling with rotations, you can think of as a translational tiling, but with more tiles. You could take it, like you can tile the space with an upward pointing triangle and a downward pointing triangle. Okay, but you can't tile just the upward pointing triangles. But anyway, so the first basic question, which is I think somewhat vaguely, is can we tell whether a given tile tiles a given set? Or in terms of equations, can we solve this equation? Okay, so given a tile F and a set E, can you solve the equation A direct sum F equals E? This one, can you tau F? Can you tau E by F? And if you can, what is the structure of the tile? Are the tilings necessarily periodic, or can you have non-periodic tilings, or what? What kind of tilings can you get? Okay, so these are imprecise questions. Here are some more precise questions of this type. Okay, so instead of talking about arbitrary groups, let's fix attention to the discrete setting and just take the lattice. Okay, just take a lattice like ZD, and take some periodic subset of ZD, maybe all of ZD if you like, and then you take a finite subset of this lattice. So maybe like 4 points, or like some finite set of points. Okay, so usually we think of discrete problems as being simpler than continuous problems. So so this is where we start. Okay, so here are 3 precise questions. So the first is logical decidability. Okay, so if I give you a periodic set and I give you a tile, and I ask you, is it possible to tile your big set by the small set? Is this statement decidable? Is it true? Is there a proof or disproof of the statement in, for example, CFC or whatever your favorite theory of mathematics is? Mine is CFC, but okay. Okay, so that's logical decidability. Closely related to that is the question of algorithmic decidability. Like, is there some computer program, an algorithm, which if you feed it a finite set, if you describe for it, here's a finite set in ZD, and here's a periodic set E in ZD, is it possible for F to tile E? And is there an algorithm, a Turing machine, if you wish, which in finite time will spit out yes or no, if and only if yes, if F can tile E, or no, if F cannot tile E. So this is the question of algorithmic decidability. And then the third question, which emerged in the 80s and then popularized particularly by Ligurius and Wang in the 90s, is what we now call the periodic tiling conjecture. So we have seen that not every tiling in the world is periodic. Okay, I gave you an example of a unit square, which can tile the space of the plane non-periodically. So non-periodic tilings can exist. But what we have observed in nature often is that whenever there's a non-periodic tiling by a tile, you can often modify it, you can repair it to be periodic. So you go back to this tiling is not periodic, but if you just take this line and you slide it back, you can create a periodic tiling from this non-periodic tiling. So this particular non-periodic tiling can be repaired into a periodic tiling. And the periodic tiling conjecture is the assertion that this is always the case. That if you have a non-periodic tiling of any finite set of any periodic subset of a lattice, then you can fix it, you can modify it to be a periodic tiling. Okay, so these are 3 concrete questions, and they're still open. These are, that's actually quite remarkable. These are like really fundamental questions about tiling that we cannot answer, but we are making more and more partial progress on these questions, and that's sort of what I want to talk about. Now, these questions are related to each other. So for instance, the first 2 look related, and they certainly are. So there's a standard argument that if a problem is logically decidable, then the class of problems that it's in will automatically be algorithmically decidable as well. So this is sort of obvious for logicians, but maybe just to go through this. So suppose that the answer to the logical decidability problem is yes. Okay, that means that given any tau F and any periodic set E, the sentence "does F tau E" is always decidable. It's either a proof or disproof so it's either a proof that it tiles or a disproof that it doesn't tile. Then, okay, with one caveat, assuming ZFC is consistent, which I will assume, then this implies that this problem is also algorithmically decidable, because the logical decidability gives you a very obvious algorithm, right? So the algorithm is that you get your computer program to just enumerate all possible proofs and disproofs of the sentence F tiles E. Okay, and so there's a countable number of possible proofs in the world. You just go through them. This is a very slow algorithm, but it will, if your question is decidable, eventually this algorithm is guaranteed to hold to either a proof or disproof that F will tau E. And so if your problem is logically decidable, then it is also algorithmically decidable. Okay, just as a side remark, this is also gives you one of the quickest proofs of the Godot incompleteness theorem, that there are sentences in the world which are not logically decidable, because thanks to the undecidability, the algorithmic undecidability of the Turing machine problem, there exist problems that are algorithmically undecidable, and hence by this argument, there also exist sentences that are logically undecidable. Okay, So that's one connection between these three questions. And the second connection, which was observed by Wang in the 60s, is that this periodic tiling conjecture would also, if this periodic tiling conjecture is true, that every tiling can be repaired to a periodic tiling, then that implies that the tiling problem is logically decidable, and hence by what I just said, it's also algorithmically decidable. Okay, so why is this? If you have a tiling which is periodic, that periodic tiling is basically a proof in ZFC that tiling exists, because you can describe, I mean, you just tile one fundamental domain, and then and that's just some finite case check, okay, and that you can formalize as a sentence, as a proof in ZFC that you can tile one fundamental domain, and then just extend it periodically. And so, whenever you have a periodic tiling, that is a proof that tilings exist. Basically, because periodic tilings can be described using sentences of finite length. The problem with non-periodic tilings is that you need an infinite number of words to describe the tiling, and so it's not a proof in ZFC. If instead you can't tile, okay, so if there's a big set E that cannot be tiled by F, E is infinite, but you can approximate E by various windows. You can intersect E with a box, and you get a finite set. And by an application of what's called the compactness theorem in logic, or you can use other compactness theorems, Tikhonov's theorem or whatever. There's a simple compactness argument that says that if you cannot tile an infinite set, then there must be some finite fragment of this infinite set that you also cannot tile in a certain sense. So there's some window such that you can't tile inside that window your set by E. And so by compactness, such a thing must exist. And then once you have that window, the failure to tile that window can be checked in finite time, and you can code it as a finite length proof in ZFC that you can't tile the window, and therefore you can't tile the whole space. So if you tile periodically, then the same is decidable. If you can't tile at all, then the tiling problem is decidable. And the periodic tiling conjecture says that those are the only two cases. Either you can tile periodically or you can't tile at all. So the upshot of all this is that we really want to solve the periodic tiling conjecture, because this would sort of solve, at least answer all three of these previous questions in the positive. All right, so what do we know about the periodic tiling conjecture? So you can phrase the periodic tiling conjecture in any group. It's completely trivial when G is finite, because everything's periodic in a finite group. That's boring. Slightly less boring is one-dimensional groups. On the images, every tiling is periodic, as it turns out. This is an easy pigeonholing argument, and it was discovered by Newman in the 70s. Slightly more generally, if you take a one-dimensional group, Z cross a finite group, so just a slight thickening of Z, the same pigeonholing argument applies actually. And tiling a one-dimensional group turns out to be very nice. It's always periodic. Although somehow that was not observed until our paper like this year. But anyway, okay, and in 2 dimensions, it took surprisingly long to settle to the 2-dimensional case. So 2 dimensions, Z2 has only been settled last year. Like, well, there was a paper about Algeria. At least when you are tiling the entire lattice Z2. And then more recently, Rachel and I, we generalized that argument to periodic subsets of Z2. For ZD, for higher dimensions, we have a lot less results. There's a result of Mario-Zegedi that the tiling conjecture is true in ZD if you assume that the tile set has prime order, or order at most 5. But that's, yeah, that still leaves a lot of other cases unresolved. Yeah, so for example, the tiling conjecture in Z3 is still wide open in general. And one reason for this is that what we do know, we have negative results too. So the tiling conjecture is a question about one tile, but the moment you introduce more tiles, we know that things start going wrong. So it is known that once you introduce enough tiles, all 3 of those questions, the periodic tiling conjecture, logical decidability, algorithmic decidability, have negative answers. So there exists some set of tiles in the world, and tiling some lattice, where there are no periodic tilings. That it is possible to tile by these set of tiles, but none of the tilings are periodic. These are called aperiodic tilings. And also, there are some set of tiles where it is not decidable in ZFC whether it tiles or not, which is a bit weird to wrap your head around, since it seems like such a simple question. Like it's not one of these questions which you would believe is undecidable because of large cardinals or something. This is a very concrete, so you can actually produce a concrete list of tiles where the tiling question is just simply undecidable. In principle, the smallest sets are pretty large. And related to that, the question of whether tilings are possible for a set of J tiles is algorithmically undecidable. It was first worked out by Berger in 1966. All right, so yeah, there are tilings that are undecidable and there are tilings that are aperiodic. And the relationship between the two is that if you're undecidable, you are necessarily aperiodic, but you can be aperiodic without being undecidable. Undecidability is a stronger statement. Here is a famous example of an aperiodic tiling in R2 now. This is called a Penrose tiling. So it's the tiles are two different rhombi, each in 5 different rotations. So there's really, up to translations, there are 10 different rhombi here. And so there's 10 specific rhombi with certain angles. They involve like the golden ratio and so forth. And, or fifth Russo unity, I think. It turns out that these tiles, they tile all the space. So it's, but only aperiodically. There was no way to take this Penrose tiles and tile space periodically. They can only tile in this sort of quasi-periodic fashion. So this is a Penrose tiling. This particular one is decidable. I mean, you can sort of visibly see. Well, okay. I mean, you can prove that these tilings exist. So it's decidable, but it's not periodic. Okay. Many of the constructions of undecidable tilings come from what are called Wang tiles or Wang dominoes. So these are tiling problems which have colors on them. So a Wang tile is it's a bunch of unit squares, like Scrabble pieces, unit squares, but where each side of the square has a color. So there's some finite set of colors, red, green, blue, and so forth. And each tile has got, there's some set of colors, each tile has got a certain color for the north edge, south edge, west edge, east edge. And so you have some finite set of these dominoes, and you want to tile space by these squares, and you just tile the usual square lattice, but the constraint that you have is that you have to match colors. So if a tile has a red edge up here, it must be matched by a tile with a red bottom edge. If it has a red top edge, the square above it must have a red bottom edge to match. So this is a Wang tiling problem. Now, this is not exactly a translational tiling because we don't have colors in our original setting. But there's an easy observation in Golem that you can replace any Wang tiles, you can replace with an equivalent translational tiling problem by basically creating jigsaw puzzle pieces where every color corresponds to a certain corrugation of the edge in such a way that the edges only match up if they have exactly came from the same color. So for example, this is an example of a tile set of 11 tiles. Wang tiles where, okay, so instead of coloring the edges, we colored triangles just to make it a little easier to see. So like this tile, we've got a green edge here, red edge here, white edge here, and red edge here. And so these are 11 tiles, and it turns out that this is an aperiodic set, that it is possible to tile space in such a way that the colors all match, but you can only do it non-periodically. There's no periodic way to tile with these colors. And in fact, 11 is the smallest set of tiles that do this. So there's this amazing calculation of Giando and Rao in 2015, computer assisted, that there is no set of 10 or fewer tiles with this aperiodicity property. That 11 is the exact minimum number of tiles here needed to make an aperiodic tiling. So this is the tile set as described using colors, but you can convert it to a translational tiling. And basically every single color got changed into an edge. So I think white, for example, so the straight edge corresponds to white. Red corresponds to a wavy edge, I think. Okay, so this was wavy edge corresponds to red edge, and the other colors have been replaced with different jigsaw pieces. And the only way, and the tiling properties of this set of translational tiles is exactly the same as the tiling properties of the Wang tiles. So because the Wang tiles have no periodic tilings, this guy has no periodic tilings as well. And you can also discretize this and make this an example in Z2 instead of R2 if you wish. Okay, and here is an aperiodic tiling by Wang tiles with a slightly larger tile set, 13 tiles in this case, as it turns out. All right. Okay. So here's some of the history. So there's a lot of effort invested in finding aperiodic and undecidable tilings. Yeah, so the big breakthrough was by Berger in 1966, who wrote this massive thesis where he constructed a set of 20,426 tiles which was aperiodic. And then that particular tiling was decidable, but his methods also show that there was an even bigger set that he didn't even bother constructing, which was undecidable. And then over time, people found clever ways to lower the number of tiles required. And so, for example, I mentioned there's a result of Zheng and Rao that uses 11 tiles using this Wang tile construction, which was aperiodic. And that's the limit you can do if you only use Wang tiles. But there are other tiles out there. There's another construction of Aman using 8 tiles, which is still aperiodic. And there's another construction of Ollinger of 11 tiles, which are not Wang tiles, which are even undecidable. So there's some weird set, there's some explicit set of 11 subsets of the plane, such that you cannot tell. It is not decidable. You cannot prove or disprove whether they tile space or not. Yeah. So one of our results is that we can morally turn all these numbers into 2 with an asterisk. Okay, so let's see. I think that's my next slide. Is it? Yeah. So so all these previous results, by the way, these were tilings of Z2. Right? So most of the tiling literature is about tiling the plane, which because it's some of the most visually appealing set to tile, and it's a Wang tiles in particular tile the plane. So what Rachel and I were able to show is that basically the whole situation is bad even down to 2 tiles. So there's a real transition between 1 tile and 2 or more tiles. But with one caveat is that we no longer tile Z2, we have to tile a slightly thicker version of Z2. So what we were able to prove is that there exists a thickening of Z2 across a finite group. So you take a slightly larger version of Z2, and then a periodic subset of that. So you take some portion of Z2 across a group, and such that and you can find 2 tiles in this slightly thicker plane, such that the tiling question is undecidable. So there are 2 tiles in this big space where it is not decidable in finite time whether the tiling exists or not. And as a consequence, what that means actually is that because you can't prove it, actually tilings must exist in the standard model of ZFC. Okay, but they might not exist in other models of ZFC. And if they exist at all, they have to be aperiodic. So none of the tilings are periodic, but they're always they exist in some universes and don't exist in others. So that's what happens. If you don't like thickening Z2 by finite group, you can instead thicken ZD by adding more dimensions. And so the same statement is true in some ZD for some large D. So there's some huge dimensional lattice and 2 tiles in that lattice where you cannot tile your given space. A periodic subset of the given space, not taken by, well, it's not decidable whether you can do that or not. So that's the 2 tiles. We can even get down to 1 tile, but then we have to cheat a lot. And the cheat is that we make our group G non-abelian. And then it turns out there's a lot of tricks you can use to actually convert 2 tiles into 1 tile. So basically, the moral of this is that the positive results are getting close to, on the periodic tiling conjecture, are close to best possible. At least the moment you have 2 tiles, things become very, very bad. But we have to cheat right now by thickening our group. We still don't know for Z2 itself whether the periodic tiling conjecture is true for 2 tiles or not. That is still an open question. Okay, so in 2 or more tiles, things are really bad. But when there's 1 tile, things are pretty good. So we also have some positive results. If you are, but so far our positive results are mostly in low dimensions. So if you are tiling with 1 tile, say a lattice ZD, in 1 dimension, it turns out the tilings are periodic, and in fact we have even a very explicit formula for the period that all tilings are periodic, and there's an explicit formula for the period which I won't repeat here, but it's at least common multiple of various shifts of the tile, basically. And also in 2 dimensions, we know that if you set tiles at all, then it is periodic. And again, there's a more or less explicit way to compute the period. And we can actually get a reasonably good bound on the period. So the period is actually polynomial size in the diameter of the tile. So not only is the tiling problem decidable in 2 dimensions, but we now actually have a complexity bound on how long it would take to verify that it is a tiling or not. Unfortunately, it's exponential time, but it's still quantitative. We also know a bit more. So it turns out that in 2 dimensions, we can prove that tilings, they may not be periodic, but they are not much worse than periodic. The worst that a tiling can be in 2 dimensions is what's called weakly periodic, which means that it is the finite union of pieces, and each piece is periodic in one direction, but the 2 pieces could be each periodic in different directions. So just to give you an example of that, here we're tiling not R2, but take R2 cross Z. So take an infinite number of planes stacked on top of each other, like a big sandwich. And on each slice of the sandwich, you take, so we're tiling, our tile is a square, and we take a tiling which is either periodic in the horizontal direction, the X direction, or periodic in the Y direction. So in the black slice of this tiling, we've decided to make a horizontally periodic tiling. In the next slice down below, which is this gray tiling, we've decided to make a vertically periodic tiling. And then you can just keep, for each slice, you just arbitrarily choose which slices. So randomly, half the slices will be vertically periodic, half the slices will be horizontally periodic. And pretty soon, if you do that, you can create a tiling of the whole space, which is not periodic in any direction, but you can split it into two pieces, one of which is periodic in the horizontal direction, and one which is periodic in the vertical direction. And that's an example of a weakly periodic tiling. So what we can prove, as I said, in 1 dimension, it turns out all tilings are periodic. Then it's very rigid. In 2 dimensions, you have some limited flexibility. Tilings do not have to be completely periodic, but they must always be weakly periodic. Then there's the 3rd thing which I'll skip. And in higher dimensions, we do not have a complete description of tilings. We are working on it. But we have what we call a structure theorem. We can at least, we have a rather technical way, non-trivial statement that if you have some tiling in higher dimensions, then that the indicator function of the tiling, we would like to say that it's periodic or weakly periodic. We can't do that, but we can split it as a function. We can write it as a linear combination of other functions, finite combination of other functions where each of the other functions is periodic in one direction. So there is something like weak periodicity, but at the function level rather than the set level, which is less strong, but still non-trivial. And in fact, the way we prove the other results is that we prove the structure theorem first, and this implies all the other positive results. I'll give one proof in this. Yeah. So the main tool in this, the reason why we have the structure theorem is because there's a remarkable symmetry about tilings. So there's something special about tilings by one tile that doesn't happen when you have tilings by 2 or more tiles. And there's an algebraic miracle, which has been observed by many people. And it's an amazing dilation invariance that suppose you can tile space, like there's some group G, and you can tile your group G by some translates of some tile F. And by using some set of translates A, and F is finite. Then you can dilate F. You can replace all the multiples of F by, you take all the points in F and you just make them R times bigger, and I call it R times F. And if F is a tile, any dilate of that F is also a tile, but you keep A the same. Okay, so you don't dilate A, you only dilate F. And so there's a weird symmetry which is not obvious. Okay, and there's one caveat. You can't dilate arbitrarily. The R that you dilate to has to be co-prime to all the primes up to the size of F. So I'll give you a specific example. The number 0, 1 tile the integers, because if you shift the 0, 1 by odd integers, 0, 1, 2, 3, 4, 5, 6, 7, they tile space. Okay, and the tiling set is the even integers. So 0, 1 direct sum, the even integers is the whole integers. So 0, 1 is a tile. What this theorem says in this very simple case is that you can dilate this tile by any odd number. You take any odd number R, and you dilate 0, 1 to 0, R, and this is still a tile by the same shifts. If you shift 0, 3, for example, by the even numbers, you will still tile space. But it's not entirely obvious why this is the case. I mean, these sets are not closed under multiplication by R. This isn't just applying a dilation. I mean, we call it a dilation lemma, but it isn't an obvious dilation symmetry. So I'll I want to give you a proof because the proof is just this beautiful application of just a little bit of algebra. Okay, so first of all, it suffices to dilate by primes. Okay, so if you take if you can prove that you can dilate by primes, big primes, then you can dilate by any shift just by the fundamental theorem of that you iterate. So the key observation is the fact that we have the Frobenius endomorphism. Mod p, a plus b for p is the same as a to the p plus b to the p. I think this is sometimes called the freshman's dream, or one of the freshman's dreams. Okay, because all the cross terms in the binomial formula just vanish in mod p. So this is true mod p, or more generally in any ring of characteristic p. A plus b to the p is just a to the p plus b to the p. So in particular, if you raise a finite sum to the power p, you can just sum it term by term. All right, so we apply this with in a specific ring, which is the convolution algebra of your group, let's say ZD, mod p. So you take all the functions in the world, but you take them values in Z mod p, and that's a group, and or let's say finite combinations, finitely supported functions, and it has a convolution algebra. You also got the group algebra. And you see the indicator function of your tile is just the sum of delta functions. It's just a finite sum of delta functions. And so if you apply this Frobenius endomorphism, what it tells you, so the multiplication in this ring is this convolution. So what it tells you is that if you convolve an indicator function yourself p times, and you work mod p, everything disappears except for every individual delta function just is convolved itself p times. And so the p-fold convolution of any set, any indicator function, is just the dilate of itself. So the indicator function of dilate is just the p-fold convolution of your original function if you work mod p. So now what we do is that we start with our tiling equation. We assume that A tiles F, so we have this convolution equation. And we just convolve by more and more powers of 1 sub F. So we convolve both sides by p minus 1 more powers of 1 sub F. And we use the fact that if you convolve 1 sub F itself p times, you get 1 sub pf. And you use the fact that convolution is associative. And you also use Fermat's little theorem, because why not? And what you conclude is that if you already tile A with F and you get 1, then you can also tile A with PF, this dilate of F, and you still get 1, but you only get 1 mod P. Okay, you don't get exactly 1. You get 1 mod P, but that's okay because this left-hand side, the convolution of A with this dilate, is bounded. It can never get bigger than the size of F. Okay, because PF, the cardinality is the same size as F. So as long as P is bigger than F, you can get rid of the mod P. Right? If a number is equal to 1 mod P and it's also less than P, then it is equal to 1 mod P. Then it's equal to just 1 without the mod P. So you can remove the mod P. I'm really fancy. I just use the left-shift principle, but that is really okay. That is really overkill. All right, and then you get a tiling. So this is I love this kind of proof. You temporarily work in finite characteristic and then you remove it at the end of the day. I'm always partial to those kind of tricks. Model theorists use them a lot. Okay, so this is dilation lemma, and you basically keep the way you prove the structure theorem is that you keep dilating and you average over all dilations, and you use things like the Algorithmic theorem or something, and this eventually gives you this decomposition. But maybe I'll skip that slide because it's a little technical. All right, so that's the tool that we've been using to get positive results. So this dilation lemma lets you somehow get 1 degree of periodicity. You get 1 direction of periodicity. And this is really powerful in one dimension because there's only 1 dimension in which you could be periodic. In 2 dimensions, it's still very powerful. And then in 3 and higher, it becomes less and less useful, and we're struggling a little bit to get beyond 2D. Okay, but now I want to talk about negative results. So if we get back and we have 2 tiles again, whether we can. Now I want to show you why these questions are hard, why they're undecidable. So the main claim is that there exists some group, some 2-dimensional group, and some tiling equation, A1 plus F1 union H plus F2 is E. And I claim that there exists F1, F2, and E such that this sentence is undecidable. We cannot prove or disprove whether this equation is solvable or not. Okay, so this is just one equation. It would be easier if instead of trying to produce one equation that's undecidable, if we can produce a system of equations which are jointly undecidable, that gives us a lot more freedom. So the first observation is that for free, if you can find an undecidable system of tiling equations, you can also find a single undecidable equation. So if there is a bunch of pairs, F1M, F2M of tiles, and a bunch of sets to tile, EM, and you want to find a set A1 and A2 that simultaneously solve all these tiling equations. So that A1 and A2, when you tile by F1 M and F2M, gives you EM. If any finite set of such equations can be converted, there's an equivalent, there's a way to convert that to a single tiling equation in a slightly bigger group. So that which means that if you can show that if you can produce a system which is undecidable, you can also produce a single equation which is undecidable. Once you have that, then you can, that gives you a lot more flexibility, because you can start thinking in terms of creating a language. So every one of these tiling equations is like a sentence in a language. And maybe every individual sentence is solvable or not solvable, or decidable or not undecidable. But if you stack a whole bunch of sentences together and you have a whole paragraph of different sentences, it could be that the entire paragraph, deciding whether there's something that obeys all the properties that you list, that may be undecidable. Okay? And so you can start hoping to have a language which is expressive enough that you can describe a very complicated undecidable statement in terms of more primitive statements, each of which has an easy encoding by one of these tiling equations. So yeah, so the strategy is to basically create a language of tilings, okay, so that you find sentences of this form, tiling sentences, each of which describe some mathematical statement, okay, each of which is fairly simple, but if you can stack them all together, you can maybe create some enormous system of equations which are undecidable. Okay, for example, in down-counting geometry, like any single quadratic equation is decidable, but if you have a whole system of quadratic equations, there exists a system of quadratic equations which are undecidable over the integers. All right. Now, how do you stack this? It's actually a very simple thing. You basically you can stack equations like a sandwich. If you have a bunch of equations like this with different tiles and different sets of each tile in a set G, you can work in a larger group, G across a cyclic group or G across the integers. So you stack several copies of your group together like a sandwich, and you can stack all those tiles together like any sequence of tiles F1, F1M. You can just put the mth tile on the mth layer of your group and just make a sandwich, okay? And you can create a single tile in this larger group whose slices are the tiles from your original problem. And if you do it correctly, you can check that this a single tiling equation in this larger group is solvable if and only if the system of equations in your original group was solvable. And so this is a fairly tedious case check. Maybe I'll skip the actual technical details. Okay, so we just have to develop a tiling language. Okay, so the first thing to observe is that tiling equations encode within them the language of functions. You see, whenever you have two groups, G and H, and you have some function from G to H, some function, that function generates a graph. Okay, so given a function f from G to H, you can create a graph, which I called A here, the set of all points x, f of x. And this graph obeys the vertical line test. Every vertical set x cross H intersects this graph exactly once. That's a tiling equation, actually. So the vertical line test is equivalent to a statement that this set A tiles G cross H using the vertical subgroup 0 cross H. So if you think of G cross H as like a rectangle, 0 cross H is like the vertical edge, the vertical portion of this rectangle. If you have a graph and you add to it this vertical set, you will tile the whole space. And conversely, it is only the graphs or functions that tile the space. So there's a one-to-one correspondence between solutions to this equation and functions from G to H. So the tiling language that we have has the ability to talk about functions. Okay, so I can now say the sentence, let f be a function from G to H, and this is a sentence in my language. Okay, of course, this by itself I'm not going to get undecidable statements just from that one sentence, but if I can add more sentences to that, like constraints on my function f. Then I can start to create undecidable statements. Now, if I have two tiles, I can actually talk about two functions, f1 and f2. Okay, so now I can start encoding various constraints. Not every constraint, but there are certain constraints on functions that I can express as tiling equations. For example, suppose I want to assert the sentence, I want my function to only take values in a certain coset. So I have a function from G to H. Suppose I have a coset y plus k of some subgroup k of H. So I have a function which takes values in the whole group H, but I want to force it to live in some coset. I have a tiling equation for that. But if I take my graph and I ask that if I sum it with not 0 cross H, but 0 cross K, if that is equal to G cross the coset, that forces my original graph to lie inside this coset. So so inside my tiling language, I can now assert the sentence f takes values in the coset. So this is now a sentence I can write in my language. So for instance, if I had somehow managed to generate many functions, so like if I have a function taking values in a big power of a cyclic group, like a d power cyclic group, that's like d separate functions, each of which take values in one factor of the cyclic group. If I wanted to assert a linear condition, a linear constraint between those d functions, that linear constraint is the same as saying that the combined function f1 to fd lives in a certain coset of a certain hyperplane in my big group. And so there is now a tiling equation. So I can now assert linear relations between functions. Okay, so yeah, linear algebra is now part of my language. Okay, now of course linear algebra is decidable. So linear equations by themselves cannot create undecidable equations, but but the hope is that you can combine these linear equations with some nonlinear equations, and then experience shows that once you have enough nonlinear equations, you can pretty quickly get something undecidable. That's the hope. Okay, so so this requires at this point you start pulling various rabbits out of hats. Well, you basically throw everything at the wall and see what sticks. But what we needed was some nonlinear. We needed the ability to express some nonlinear sentences. So one such sentence is that I want to say that there's a function that only takes values from -1, only takes values -1 and 1, but not any other value. So let's say in a cyclic group Z1 NZ, I want to say I have a function that only takes values -1 and 1. And for technical reasons, I needed to be alternating. So I have a rather weird sentence. F takes values in -1, 1, and there's a certain shift. And every time you shift by H, it flips sign. So if it is +1 at X, it must be -1 at X plus H. So if it is anti-periodic in one direction and it takes values in -1, 1, that is a sentence I can encode. Because if I have a graph of a function and I shift it by H horizontally, if I have a function and I graph and I shift it horizontally, and the union of the graph and the shift, if I ask that this be G cross -1, 1, that can only happen if your function takes values in -1, 1 and it is anti-periodic. Because if it was 1 somewhere and you shift it, then the value at this new point has to be -1 in order to fill out all of G cross -1, 1. So okay, so from this tiling equation, I can basically talk about Boolean functions. I can talk about functions that take values in -1 and 1. There is this anti-periodicity, but there's a trick to get rid of it, which I won't talk about. But I now have a language which has got Boolean functions in it, which is great because Boolean logic is beginning to sound like something which is going to be undecidable. All right, and yeah, so we can now encode in a language Boolean functions, and you can think of say +1 as being true and -1 as being false. Now we know in Boolean algebra that if you can encode the basic operations, the basic gates and, or, not, then you can encode all the other Boolean functions as some finite combination of these basic gates. Because we already can do linear algebra, we can already encode not. Right? Not right? F1 is not F2. That's just a single linear equation. F1 plus F2 equals 0, actually. So I have the not equation. Okay, but not by itself is not enough to generate very much something interesting. So you would like the other gates as well. Okay, so we want things like and or. Okay, so it turns out you can't quite encode and you can't quite encode or, okay, but you can encode something which is close enough. So if I have 3 Boolean functions, so functions that take values from -1 to 1, I can encode the sentence that F1, F2, F3 are not all true or not all false. So like there's 1 true and 2 false, or two true and 1 false. That's more complicated than and or, but it turns out to be good enough. The reason is that you can encode that as a linear equation involving a 4th Boolean function. See, if you have 3 functions taking those -1 to 1, and you require that there's a 4th Boolean function so that they all sum to 0, that can only happen if the first 3 functions are never all +1 or never all -1. Because if these functions are +1, +1, +1, this has to be -3. And that can't be, that's not a Boolean function. So throwing in a 4th function and asking this, imposing this linear constraint here gives you something like an and or gate. It's a ternary gate, but it turns out to be complete enough. Okay, that with some additional tricks, it's almost as good as and or. And then basically after a few rather routine tricks, you can encode any Boolean constraint. So if I have a finite number of Boolean functions and I have some subset of values that these Boolean functions can take, so some subset of the n-dimensional Boolean cube, I can make any constraint, not just a linear constraint, which is what we could do before, but any nonlinear constraint between n Boolean functions turns out to be encodable as a system of tiling equations by modifications of the tricks that I just showed. Okay, so now we can do all Boolean assertions. Now, Boolean algebra is still decidable. So we're still not done yet. Okay, and basically the problem is that everything we've done so far is mostly pointwise. We have developed a language that can compare the values of different Boolean functions pointwise at every given x. But in order to create a more powerful language, we need to somehow make the values of different points talk to each other. And this is where the first time we're forced to use 2 tiles. We have not figured out a way to make points talk to each other without having to use 2 separate tiles. And this seems to be the fundamental difference between 1 tile and 2 tiles. So the really fundamental example is that if you have 2 Boolean functions and you want to say that one function is a shift of the other, or say negative the shift of another, I can do that by a tiling equation, but I have to use 2 tiles. So each of these functions generates a graph. F1 has the graph A1, F2 has the graph A2. If I ask that the shift of A1 union A2 without the shift, if one tile, if the graph of one function union the disjoint union the graph of another function is equal to G cross -1, 1, that's equivalent to saying that one of the functions is negative the shift of the other function, if you think about it. So you can start encoding, you can start letting the functions talk to their neighbors, but you need the second tile. And we haven't figured out how to remove that second tile. So to summarize, with all these tricks, we have now created a language which can talk about arbitrary Boolean functions, any finite number of Boolean functions. You can impose any number of pointwise constraints, linear or nonlinear at any given point. And you can also constrain one function to look like the shift of another function. So you can also constrain nearby functions, the values and nearby values to talk to each other. Okay, so and you can do any number of Boolean functions. So you can also talk about functions that take values in any finite set, because any finite set you can encode using some finite number of bits. Okay, now this is enough of a language to encode the Wang tiling problem. You see, remember, recall that we have these Wang tiles, which are sets of squares with different colors, and there are ways to tile them together to make undecidable tilings. Now, the Wang tiling problem you can encode as a collection as a set of constraints about functions. So a Wang tiling, what it is, so there's a set of colors, and at every given square, in your lattice, you have a color for your north edge, south edge, west edge, and east edge. So you have basically 4 color functions on Z2. And you have a specific set of tiles you're allowed to use. And the constraint that you can only use those tiles is a constraint that at every given location, the north, south, east, west colors have to lie in a certain set. So there's some nonlinear constraint on the color set. So that's one condition. But also the colors have to match. So the domino condition is things like that, for example, the north color of n has to equal the south color of n plus 0, 1. And so these are what the constraints that define a Wang tiling. And these are the constraints that we have developed a language to express. And at this point, we just use the existing result that there exist undecidable Wang tilings. Okay, so someone already did the work and constructed a set of Wang tiles, which is undecidable. The equations of Wang tiling can be converted after a lot of work into a tiling system using 2 tiles. And so therefore, there are tiling equations involving 2 tiles that are undecidable. Okay, so that is where we are so far. We're still working on this problem. There are still many open questions. As I said, the periodic tiling conjecture is open for pretty much any group bigger than Z2 we can't answer. So Z3 is open. Z2 plus a cyclic group. We have some partial results. If a cyclic group has prime order or like 2 primes, I think we can solve it. But we're still working on the general case. Yeah, we can make undecidable tilings with 2 tilings. We're beginning to suspect that in high enough dimension, the periodic tiling conjecture, even for 1 tile, is probably going to be false. But we don't have a construction yet. We're looking at that. As I said, we have this is annoying issue dependence force us using 2 tiles. There's a technical condition. Right now, our undecidable tiling equation only tiles a subset of G. We'd like to tile all of G. And most of our results are in the lattice CD. We would love to have analogous results in the Euclidean space. And there's some technical issues. You have to specify what kind of measurability your tiles have. Turns out that whether you are Borel or Lebesgue measurable actually makes a difference. So anyway, but yeah, so many still open questions. Yeah, so that's sort of the state of the art of translational tilings. Thank you very much.
Thank you.